So let's get us started, and welcome back here this morning. I'll begin here by taking a quick look at the syllabus. Obviously, the last time we met, we did a test, and obviously I don't have it graded yet. I need more time than that. So I will get working on that this weekend, and Friday, Saturday, Sunday, I should have time to get it done, and I'll pass it back on Monday. If I get it done earlier than late Sunday night, you might want to check your pipeline account. I'll send out an email with a link that will then be a Google Doc, and then you can, it'll be a spreadsheet, and then you can look up your K number and scan across and see your score if you want. Or you can just wait till Monday morning. And so Monday morning come, and we'll just kind of lay them out there and grab them as you come in, and we'll kind of look at them real quick. Now, with that said, you might remember that we put off that first test so that we could use the overflow room, and that worked very successful. My concern about that has always been, and continues to be, that since you were focusing on the first test, you may not have done much with Chapter 5 as of yet. I know some of you have been working 5 as I've been giving you my input to that, and I think you'll be glad you did, because now looking ahead, you'll see that it's not that long before we have exam number 2. And so exam number 2, not to panic yet, but is March 16th. And so it's, not next Monday, and not even the Monday after that, but the Monday after that. And so these 4 chapters, considering we've pretty much already done 1 chapter, are going to come pretty quickly. Anyways, that's the syllabus, and just wanted to kind of keep focusing on that. So we've done Chapter 5. We were doing examples from 5. I think it'll serve us well to continue to do some examples from 5, and then get started with the lecture material in 6, and then next week we can get into 7, and the week after that is 8, and then we can have a test on 5, 6, 7, and 8 on Monday the 16th. So that's the game plan. And so like I said, hopefully you've got a chance to start to work on them. Let's do some more. I think we left last time before the test, so the Wednesday, and we were looking at it, and we had just kind of set up number 26. So, or did we do 26? Maybe we completed it. Yeah, I think we just kind of set it up. Yeah. So let's go back to that. Let's set it up again, and let's go through those 4 steps. And maybe we won't spend as much time today then on that last step, solving the math, but at least those first 3 are the big ones, right? Got a good physical picture of what's going on? Write out the free body diagrams, because that's going to help you for the big step. Step 3, write out the equation. Use Newton's laws of motion, particularly the second law of motion, and write out a system of equations. Okay, and then the last step is to solve that system of equation. All right, so the pictures usually help, and so here's a picture. You can kind of see that we got a heavier weight 9 and a lighter one 5 kilograms connected together over a pulley. And this says then a 5 kilogram object is placed on a frictionless horizontal table. It is connected to a string that passes over a pulley and then is fastened to a hanging 9 kilogram object as shown in the figure. First part says draw the free body diagram of both objects. All right, I guess it's good that they say that, but let me emphasize, if they don't say it, do it anyways. All right, it'll really help your thought process. So we've got 2 objects. I'm going to do the free body diagram for each of them. And obviously, or maybe it's not so obvious, but I would need both of these. You cannot solve this without only looking at one object. Obviously, the behavior of this would be depending on both blocks. Obviously, how much this one is and also how much that one is. All right, so coming over here and calling this the 5 kilogram block. Let's go through all the forces on the 5 kilogram block. Actually, maybe I should pause and go back to step 1. Do we have a good physical picture of what's going on? I know we did this and talked about the acceleration, but it's worth mentioning it again, especially as this leads into the next problem. This one goes down, say 1 meter. What does this one do? Moves over to the right 1 meter. And so if I were to write the movement of block 1 and the movement of block 2, they are equal. So I'll call it R1 and R2. The reason that's relevant then is if I take the derivative of both sides, if I can squeeze in a derivative, wouldn't that say the speed of block 1 is the same as the speed of block 2? And then if I took the derivative of both sides yet again, wouldn't that then say the acceleration of block 1 is the same as the acceleration of block 2? And that's important as we go to set this up. There's not two different accelerations, although one goes to the right and one goes down. They have numerically the same acceleration. And that is what we get from the step 1, a good physical picture of what is happening in the process. And so I should have emphasized that. That's step 1, because then step 2, we come over here and we start drawing this free body diagram, and we say, all right, what are the forces? And it's everything touching it plus gravity. And so maybe I will start with gravity. Let me call this M1G. Everything touching it. Well, the tabletop is touching it, so that will be normal force. It says it's frictionless, so there's no left-right friction. Okay. So that's one thing touching it. And of course, the other thing touching it is that string. And so I'll put tension T. And so there is gravity and everything touching it. All right, so there's my free body diagram for object number 1. Now, object number 2. Same idea. Gravity plus everything touching it. So gravity is M2G. And the only thing touching it is that string. And so, okay, there's what they asked me to do. But as I'm trying to emphasize, whether they ask it or not, draw the free body diagram or diagrams as the case may be. Because that will help us on the big part. It's this step 3 then. Can you take these ideas of the physical picture and the forces on them? So step 1 and step 2, and can you write out a system of equations so that then you can solve for whatever they're asking for? And I don't think I finished reading the question, but it does say, find the acceleration of the two objects, which we just argue they would be the same value, so that's really one question. And the tension in the string. So there's the other part of the question. So I'm going to go ahead and write it out. Why don't I start here? Now on this one, if I use the conventional coordinate system where x is to the right and positive y is up, when I look at that, I would say, all right, the sum of the forces in the x direction have to equal the mass times the acceleration of it. Now in this case, the only thing in the x direction is the tension. The mass is 5 kilograms, and I would get an acceleration of A. I'll put a box around it to say, okay, that is one equation. Of course, it has the two unknowns, the tension and the acceleration, but that's perfect. That's exactly what the question is asking. Find the tension and find the acceleration. All right. Also, if I do the y direction, and as you gain experience, you'll see that in this case, the y direction is going to be pretty useless. Maybe I should have put acceleration of object number 1 in the x direction back there on that first one. Because as I look at the y direction, I would see I have a normal force up. I have weight pushing it down, which would be 5 times 9.8. And so there's my mg right here, pushing it down. And of course, what is the acceleration in the y direction? 0. That would tell me the normal force then is 49 newtons. Okay, that's great. Usually I need normal force if I need to calculate friction. That was part of the normal force, was part of the formula for friction. So, although it's useful, I guess, to know it, it's not really relevant for this particular question since I don't really need to know the normal force. So, I did it maybe just for completeness. And that's what I was alluding to, that as you gain some experience, you kind of would have seen that ahead of time, that there's real no point in doing the y direction. But I think it does help your understanding of getting these 4 steps down. If I do the same kind of logic for the other object here, the other free body diagram, I would say the sum of the forces. Now, if you want to say the y direction, that's fine. But I hope you also see that the motion of this one as it moves in the x direction matches the motion of this one moving down. So I would suggest that we don't call them y's, just to make our thoughts a little bit easier. But I like to say, why don't we call that downward the x direction? So when this one moves to the right x, it corresponds to, it's a terrible x, corresponds to this one moving down in the x direction. And so then I'll call that a y. And that helps me. And if it helps you, great. I don't know. I mean, it is a little different that we change our coordinate system. Not only are we calling the vertical on the x-axis now, but we're calling down positive. But like I said, I like that only because if you come back here, didn't we say they had the same accelerations? And if you're going to say that, then down here has to match positive with over to the right. If you were calling this a negative direction and this one a positive direction, then you would have to say the acceleration of this one is the negative of the acceleration of that one. And so there's nothing wrong with that. It just got to make sure it's real clear what you're doing in terms of your diagrams. And you can't just blindly kind of plug and chug into here. Make sure, again, I guess it's been a while since I said it, read the math. Understand the meaning behind it. If you find yourself, just plugging and chugging, you're going to get some things right and some things wrong. You're going to get a lot of things wrong. I guess you'll do okay. You'll get a okay grade, okay score. You'll transfer to an okay school. You'll have an okay career. You'll meet an okay spouse, and you'll have okay kids. All right? But there's a lot more behind it. It is not a math class. There's a meaning behind each step. And the better you can know the meaning of the math. And so this is an applied math type of course. And in fact, it probably is the most applied math course you've had. The most math, well, other than a math class itself, of course, but in terms of actually using that math to do something besides just math. And that that to be done creatively, you have to understand the math. All right, so that's going to be my approach, and you can decide if you like it or not, but I recommend it that when this moves x, then this one moves x, and so then I can just simply say, not only do they have the same acceleration, but they have the same axes. X goes with x, and the plus goes with the plus, and I don't have to worry about a plus going with a minus and all that stuff. So to me, that's worth calling downward an x direction. So with that in mind, I would say that what I really am interested is the sum of the forces in the x direction. Again, now the x direction is vertical. And that would have to equal mass 2 times the acceleration of number 2, and it is in the x direction. And so when you come over here to do that, you could say, well, what's pulling it down is its weight. That would be a 9 times g. And what's pulling it up is the tension. And so again, notice that downward, the weight is a positive number. I'm calling down positive. And the upward is a negative number. And of course, that would have to equal to 9 times the acceleration. And that's kind of nice here. That acceleration A is the same as that acceleration A. And so calling that a positive and matching it with that as a positive. And so now if I make a little box here, again, now you can see I have a second equation. And so here is what no doubt you learned in your algebra class, a system of equations. 2 equations, 2 unknowns. And so that can lead to step 4. And here's where I think I'll save a little bit of time so we can look at other things and say, step 4 is solve them. And whether you choose to solve them by substitution, this seems like a perfect substitution because we have t equals, and then we can just put that straight in. Or you could do elimination. And actually, this would be pretty good for elimination too. It's set up perfectly for each one. You can do a little matrix with the Kramer's rule if you want, but I wouldn't. It's not that complicated for that. So, but again, two equations, two unknowns, and now you've got your tension and you've got your acceleration. Fair enough? So let me shift gears then here. Let's try another one. Again, let's run through these 4 steps and probably just skipping on the last one, but 32 is a lot like this with added complexity. And so let's read 32. And like all these problems, the first thing is, do you have a good physical understanding of what's going on? That will help in answering these questions like, how are their speeds and their accelerations related here? And so, number 32, take a look at the pulley system. It's going to take some imagination on your part to go, okay, now how are those pulleys connected? What is happening here? But let me begin by just reading it. It says, an object M1, right here, is on a frictionless horizontal table. It is connected to the object M2, okay, right here, through a very light pulley, P1, and a light fixed pulley, P2, as shown in the figure. If A1 and A2 are the accelerations of M1 and M2 respectively, what is the relationship between these accelerations? So of course the first thing they're trying to get you to do here is start to ask yourself, do you really understand the physical picture of what's going on here? How are these two related? I lost my blue pen again. Well, maybe I set it up here. But anyways, back here then, how are these two related? Well, let's talk. What do you think would happen if this one went down 1 meter? Okay, you're beginning to see that it would pull on this string, wouldn't it? Which would then pull this pulley over. And let me stop right there. Okay, so if this goes down 1 meter, well, what is it going to do to this pulley? It's going to pull it 1 meter, right? In fact, let me kind of draw at least that much. I mean, they do a good job of drawing the picture, so I'm not sure I should repeat the whole picture here. But there's the pulley, here's the string going around, here is M2, and as M2 goes downward, which let's call this movement R2, okay, so it moved down, R2. This first part of it, I'm hoping is very clear that that pulley, P1, is going to move over the same distance that this block moved down. All right, so I would say the pulley, the movable pulley, moves over R2. But what I really want to know then is, how does that affect block number 1? Does block number 1 move over the same amount, R2? Maybe it would help to draw a little more here for our table. It might be helpful. What if I imagine, this is not how it's set up, but see if this helps. What if you imagine this right here being a bungee cord instead of a string, so it can stretch, and that this is bolted into place so it can't move? So in other words, if this went down R2, wouldn't this move over R2? So wouldn't the bungee cord stretch by how much? Wouldn't the bungee cord have to stretch by twice R2? Right? Bungee cord would stretch here and here. So in other words, for this block to stay where it is, the bungee cord would have to have grown by twice R1. Now, of course, it's not really a bungee cord, so what would happen instead? It would move over, right? The string here would move over and fill in this spot right here. So how far would this have to move over? 2 R2. So the distance that number 1 is going to move is twice the distance that number 1 has to move. And so there's the piece of mathematics I was trying to get from the physical picture. What is the movement of number 1 compared to the movement of number 2? So they have a 2-to-1 ratio. And so most of you saw that right away, and so that's good. I heard a bunch of halves, so I think you had the 2-to-1 ratio, but got it flipped there. But that number 1, moves twice as much as number 2. Knowing that, what if I took the derivative of both sides? And I mean the derivative with respect to time. What would that tell me? Well, they don't have the same velocity, right? They tell me that block number 1 moves twice as fast as block number 2. And that makes sense because it's supposed to move twice as far. So in order to do that in the same amount of time, it better move twice as fast. And if I take the derivative yet again, I will get the answer that they are looking for. And one you'll need to answer this question is, how does the accelerations of these two compare? And that's an important piece. And I think a more complicated piece than we saw back on the last problem. And so instead of having a 1-to-1 ratio, we have a 2-to-1 ratio. And we need to figure out which one is bigger than the other. All right, so I think I'm getting step 1 accomplished, which is got a good physical picture of the motions that are involved here. What's going on? And I would say by far, this has the most complicated of motions we've seen so far. Okay, and so I'm feeling good about that one. That's okay, they're both going to move. This one moves to the right, this one moves down, but this one moves twice as far, has twice the acceleration of that one. So that's what I got out of step 1, the physical picture. Now let's go to step 2, the free body diagram. So free body diagram, I come over here and say, okay, what is my free body diagram? Well, let's use, say, number 1, and maybe in my drawing up here, I'll match what the author has for object number 1. And again, it's the gravitational force and everything touching it. So in this case, it is an M1G. There's the gravity. What's touching it is the normal from the table. And they said it was frictionless, so we don't have to put a left-right component to that force. All right, just all normal. And then there is this string. Now, unlike the last one, don't we have 2 different strings? And so I'm going to go ahead and call this T1 because that doesn't necessarily mean it is equal to the tension in the other string. And so I think I'm done with the free body diagram then for that object, right? Gravity and everything touching it. Whereas the free body diagram over here for object number 2 would be then gravity pulling it down, so I'll call that M2G, and the tension pulling it up. And again, it's a different string, so it may or may not be the same tension. So I'm going to put a T2. And so clearly this is a little bit harder. But like the last one, then, let's go to step 3. Let's write out the equations. And so I will need a coordinate system, and I'll start with the first one and use the traditional. To the right is a positive x and up is a positive y. But knowing that, then for my second object, and to put x's with x's, I'm going to go ahead and say the axis pointing down is my positive x axis. That way, I know x goes with x, and positive goes with positive. In fact, the way I have it written right here, I have already begun to set up positive goes with positive. So if I'm going to use this equation, I better make sure my grid matches positives with positives. If I don't change my grid here, I could have positives here matching negatives here, which would not match this equation. And so the equations I write out would not match this equation. And so when I tried to solve it, I would have all kinds of troubles. Don't got my signs matching up. All right, so this is kind of that clue that I've already started matching positives with positives. All right, well, let's go ahead and then write out this equation. I would start off with the sum of the forces then in the x direction. And in this case, there is only one force. It is T1 in the x direction. And then that would have to equal to M1 A1. And are we told? What are we told? Oh, so this is all symbols. We're not even told. It's just an M1. It just says here, if A1 and A2 are the accelerations of M1 and M2, what is the relationship between these accelerations? And that's what we just answered. And then B, the tension in the string and the accelerations. So we want, again, solve for accelerations and solve for tensions. So we got a little bit of work to do, but I think this is a good first step right there, right? There it is, an M1 and an A1 and a tension. That would be the connection I would get between tension 1 and acceleration 1. The vertical direction, maybe I'll put up here for completeness like we did in the last problem. However, we've got the normal force going up. We've got M1G going down. That has to equal mass times the acceleration of number 1 in the y direction. But it's not accelerating in the y direction, so that has to equal 0. So that tells me then that the normal force equals M1G. And although that's true, it's really not of much use here, so I'll just put a little dotted line around and say, okay, that's fine, and that's true. Not useful for what I need to solve. I need things that connect T1 and T2 and A1 and A2. That's my connections here. All right, so that would be free body diagram for number 1. Looking here at number 2, same idea. I could say, let's write out the forces in the x direction. Now remember, on this one, the x direction is the vertical. So in this case, I would have gravity pulling it down, M2G, and the tension, T2, lifting it up. What does that equal? Well, I guess it would be mass 2 times acceleration 2. All right, so again, here is step 3, writing out the equations. And step 4 is solving this. Maybe I'll get a little bit started. Maybe I don't know, maybe I should do the whole thing. I do want to save time for other problems in here, but this one is worth talking about here because I have how many equations right now? 3. So if I was asked to say solve for, and that's what they're asking, A1 or A2 or T1 or T2, I mean, how many variables do I really have up here? I mean, maybe I should start writing them out here, right? There is the A1 and the A2. There's the T1 and the T2. You might say there's an M1 and an M2. I'm not sure if I'd call those variables as, you know, but they're not really given numerically, but there's symbols there. And I might even say a G is in here. But I think what the author is trying to say here is he would like for me to write out A1 equals. He wants an equation here, right? And the equation should have what in it? Well, I guess it should have these only because that's what's given in the problem. I shouldn't have the equation that says A1 equals in terms of other though. I mean, otherwise I'd be done. I mean, right? This is not what the author wants, right? He doesn't want to say A1 equals 2A2. You're not done. I mean, he wants you to write A1 equals, and there should be some equation for the acceleration of A1. And it should be in the terms of what's given in the problem. And what's given in the problem is things like mass 1, mass 2, and G. And so that's really what I think he's trying to say. Now, the reason I bring that up here is I would want to eliminate that, and that. 3 unknowns. How do you eliminate 3 unknowns? Well, let's see. You start doing algebra. If you have 2 equations, you can do a substitution of those 2 equations. Won't that eliminate an unknown? All right, so if you have 2 equations, you can get rid of an unknown. Now, if you had 3 equations, couldn't you get rid of 2? And there's my dilemma. Isn't that what I have? How many equations do I have? 1, 2, 3. If I start putting these together, how many variables could I eliminate? Just 2, right? I can eliminate 2. Right? Now 3 equations can solve for 3 unknowns, right? But I can only eliminate 2 when I combine these together. And I need to eliminate how many? You see a problem here? Don't spend hours working on this yet. You're not going to get anywhere. You don't have enough information for a solution yet. That's my point. You need to recognize that. I've done everything correct so far. I've got that equation, I've got that equation, I've got this equation. Great 3 equations. But if you start combining those 3 equations together, let's say these 2. If you combine these 2 together, maybe you want to eliminate A1. So if A1 is out of the picture, then you can maybe put these 2 together. And then maybe you can eliminate A2. But what you have left still has a T1 and a T2 in it. That wouldn't fit the idea of solving for T1. Because you would have a T2 in it. This is not complete. We need another equation is my point. You cannot eliminate the 3 variables without having yet another equation. Okay? So every time you combine equations, you eliminate a variable. So that is my long way of saying I'm not ready for step 4 yet. I'm not ready to solve these. Don't waste your time working on all this. You're not there yet. So I need another free body diagram. I need something to connect. I need another equation. Any suggestions? Yeah, that movable pulley, right? And so if I come over here and I take this movable pulley, I will notice that the T2 is pulling it to the right, and the string has wrapped around T1 and T1. And so essentially it's the same string, but because it is wrapped over on itself, it's the string's pulling on it twice. All right.
Why don't we shift the coordinate system so x is down again? why are we leaving it so it's to the right?
Well, I guess I have not decided what coordinate system I'm going to use for this one. Is that what you're saying?
I think so.
Yeah, so let me ask you, what coordinate system do you want me to use? Yeah, I would use the traditional one. Because again, I kind of want all these connected together. So when this goes down, this goes right. And what does this do? Goes right also. Okay? So the movement of this one, x, is matching the movement of this one, x, which is matching the movement of this one, x. All right, so using the traditional coordinate system, I could then say, let's add up all the forces in the x direction, which in this case would be a T2 in the positive direction minus 2T1 in the negative direction, and that has to equal what?
0.
Why 0?
Very lightweight, so not.
Right, it equals mass times acceleration. And it said it's a very light pulley, so I'm going to put a 0 in for its mass, and that's going to give me the 0. It does have an acceleration. In fact, we said that at the very beginning. Doesn't this object have an acceleration that would be then the same as this one? So the acceleration here would be an a2. If you would like me to put 0 multiplied by a2, I will. But of course 0 times a2 is 0. And so what I get here is T2 equals to twice T1. Ah, there we go. There was my whole discussion. Making sure I was understanding the math and reading the math. I've got 3 variables I got to eliminate. I will need 4 equations for that. I now have a 4th equation. Now I am in a perfect spot to go into the next step, which is solve these equations. Combine them together, eliminating variables as we go, so that eventually we have an equation that says something like A1 equals, and it just has an M1 and an M2 and a G in it. And so I will, whoops, I erased my first equation. Let me put that back here on the board. What was it? A1 was twice A2? Or was it the other way around? Let's see. A2, yeah, okay. So there's our 4. So the first one we came up with, then these 2 from the free body diagrams of the weights, and then this one, we had to make sure we needed another free body diagram when we looked at the pulley. So there's my 4 equations. And so maybe I will just actually substitute that one into here first. I think that's a good first approach. It'll say T1 is then equal to M1 times A1. Now, according to that, A1 is 2A2. So, again, taking these 2, combining them together, I've eliminated A1. Okay? And I've got this. Now, depending on how I want to approach it, maybe I'll put that one into here. Or would it be shorter to go there? Well, I'll just follow in order here. Let's do this. Let's solve that for A2 and put it into here. All right, so T1 over 2M1 would be A2. That's what that was saying. And if I take that and put it into here, I would get an M2G minus T2 equals M2. And then times this A2 would be T1 over 2M1. So that's what I get when I substitute those 2 into that 1. That would be eliminating A2. So again, notice what I have here. I've eliminated both the A1 and the A2 by the time I get here. Then, of course, now I have that equation, and I can put this with the fourth equation. Or maybe I should phrase it the other way around. Why don't I, since this is already solved for T2, I'll take the T2 and put it into that one. And then that'll be gone. So this will become M2G minus, and in place of T2, I will put 2T1 equals M2T1 over 2M1. And so there is, getting to my final equation, an equation that just has a T1 in it. I've eliminated the other three variables. And now I can solve this for T1. So this becomes an M2G equals, and I'm going to write this as an M2 over 2M1. And then when I bring this to the other side, it becomes plus 2T1. Maybe I'll get a common denominator before I start dividing things over. So 2M1 would be the common denominator. So I would, let's see, multiply by 2M1 in order to get T1. And now then I can finish by getting T1 by then multiplying both sides. So this is a 2M1 M2G, bringing that over to here, and then dividing it by an M2 plus 4M1. Did I? A lot of algebra there. Did I make any? I think that's right. And so there is T1. Now things start to fall in place real easily because I can get T2 by just noticing T2 is just twice T1. So T2 would be twice that. So that would be 4M1 M2 over G. M2 plus 4M1. Yay! And I can get A1 fairly easy here by realizing it is T1 divided by M1. So A1 would be this, T1, and now I divide it by A1, that one's going to go away. So it's 2M2G over M2 plus 4M1. And of course I could also get A2, because this says A2 is half of A1. So A2, taking half of it, would then eliminate that 2 up there. And there's the whole thing. And I guess I said I wasn't going to do quite the whole thing in step 4, but this was a harder one. It involved quite a bit of mathematics there, and probably was worth our effort to go through. Fair enough. Well, that was 26, or was that 32? Yeah, it was 32. 32. Let's try 42. And I hope you're beginning to see what I was saying earlier here is that these 4 steps will solve every problem. Just write out Newton's second law and solve them. In fact, would you like to know the answers to all the homework problems this weekend? Shall I give it to you now? All right, so add up all the forces, set it equal to MA. There you go. And that is all you'll do for the 40 hours it will take you to get through the homework problem, right? It's that simple. But I'm hoping you do see that big picture. That is this whole idea of chapter 5. And I should even say chapter 6. If you'll notice, every single problem we've been doing has been moving in a straight line. Nothing has turned. Well, that's why we're going to have chapter 6 for, right? And we're giving you the what I'll call the simple cases of Newton's second law, where there's more to it. An object can not only go faster and slower, it can also turn. And so that's what we're going to see coming up here real soon. All right, well, let's try this one. What number did I say this was? A 42? So number 42. Again, let's read it together so we got a good physical picture of what's going on. Then set up the free body diagram, or diagrams as the case may be. And then let's write out the equations, and then let's solve the equations. All right, so looking here at 42, it says 3 objects are connected on a table as shown. All right, so here are the 3 objects. The rough table, rough table. Friction, right? And so let's keep that in mind. We've been doing a lot recently without any friction, but this time we have some friction. So rough table has a coefficient of kinetic friction of 0.35. The objects have a mass of the 4, the 1, and the 2 as shown. The pulleys are frictionless. Draw the free body diagram for each object. Good. I'm glad they asked it, but even if they didn't ask it, draw the free body diagram. A, determine the acceleration of each object and their direction, and then B, determine the tension in the 2 cords. So kind of the standard question, what's the acceleration, what's the tension? Okay? In fact, maybe you could begin to see what you think would happen here. I mean, what if, let's say, this block wasn't even there, and it was just one big string? What do you think would happen there? Yeah, this one being a little heavier than that one, I would expect it to be pulled down. So as this one went down, this one would go up, right? Of course, it does have this here in between it. So what do you think this will do? Yeah, I don't think it would change the direction to make it go that way. I think basically it's just going to make it go less rate in that direction. And so it's going to have some rubbing going on here. That's one reason why I would think it would still go this way, but with a less effect because of the rubbing, the friction, if you will. But also, just because it has more mass, you're not lifting it up like this one, so it's not a force that is opposing this one from going down, but it is an inertia that is opposing it from going down. So for 2 reasons, I think this added one in here is going to resist this one from going down, but that just gives it a lower rate. It's still going to go down. So I think I understand this quite well, that what's going to happen is this goes down and this goes up, and then this moves over to the left. Fair enough? Now let's talk about the numbers here. What if this went down 1 meter? What would you expect about this one? 1 left, 1 meter. All right, so they're going to move the same distance, meaning they're going to have the same velocities, meaning they're also going to have the same accelerations. Okay, so that could be very helpful. There's not acceleration 1 and 2, there's just an acceleration. This one's down and this one's left. How about this one? Right, go up 1 meter. If this went down 1 meter, this goes left 1 meter, this goes up 1 meter. So this, I would say, has the same velocity and the acceleration as these other 2. So again, there's not 3 different accelerations here. There's just one acceleration numerically. Just one block goes down, one block goes up, and one block goes left. Well, let's write out our grid so that those are all the positive x direction. And so we can say they have the same acceleration in the same direction. Okay. All right, so I think I've got step 1, right? Good physical picture of what's going on. Now I understand to a point that now I can draw these free body diagrams. So let's go free body diagram for the 4 kilogram. Let's do the free body diagram for the 1 kilogram. And then free body diagram for the 2 kilogram. All right. And so my first steps here are, what are the forces? And my suggestions to you was, look for anything and everything that is touching it plus gravity. All right. Get a better wet rag here. All right. So in this one here, I have, let me call it M1G. There's gravity. And everything touching it. Well, again, in this one, there is just that string on the left. But notice, again, like the last problem, there are two strings up here. So there's a tension in this string and a tension in the other string. They may or may not be the same. In fact, as I look at the problem a little bit closer, I'd say for sure they can't be the same. Because if they were the same tension, this block would be pulled left and right. What would be the net force left and right? Right, 0. And it would move. So then we know then that this tension, which I'm going to call 1, has to be a little greater than this one in order to pull it. Or maybe even a lot greater because there is some friction pulling it. I suspect, though, it's not going to be accelerating by very much. So that makes me think the tension's only a little bit more. But it's also got to overcome the friction. So that makes me think it's going to be a lot more. But nonetheless, T1 is definitely different than T2, and it's bigger than T2. The middle block, I think, might be the hardest one here in the sense that it's got the most forces on it. Again, the first thing to do is to say, well, there's gravity and then everything touching it. So let me call that M2G, but everything touching it. And so what's touching it? Okay, definitely the table, so normal force, good. What else? Obviously the two strings, right? So T1 to the left and T2 to the right. Anything else? Yeah, and this one, there's the friction, which is also coming from the table. And so back when we said what's touching it, the table is doing two things, if you will. It's really one force, but these are the components of it. It's a normal force and then the frictional force. All right, so I think we got everything touching it. String 1, string 2, table, and then gravity. And the table we've represented with its components, how much up and then how much to the side. Now notice I gave a direction here. It's opposite to the direction it's moving. And I needed then to kind of understand that step 1, what's going to happen here. It's going to move to the left, and so that's why I put a little bit of friction there. All right, so that's probably the most forces we've had on any object so far. So 5 forces. Let's jump to the last one. So the last one, let me call it M3G. So there's gravity pulling it down, and the only thing touching it is string number 2. And like you've seen me do for this last 50 minutes here is let's choose a grid, a coordinate system. I would suggest for this first object we call downward the x direction, the positive x direction. That's which way it's going to move. That way I can put the left here, the positive x direction, and so my x motion here will match my x motion here. And so when I say the acceleration of this one and this one are the same, that is showing in my grid. It's not only the same numerical value, it is the same axis, the x-axis. Yeah?
Dr. Young, so just by indicating on the axis that your positive x-axis is now going to the left there.
This one, yeah.
Yeah. That's enough that'll be satisfactory for like on an exam if we want to show that.
Yeah. And I would encourage you on the exam, to show me which way you're calling positive. Otherwise, I mean, if you don't, then I kind of read in your mathematics which way you are calling positive. And yeah. And so you haven't got back your first test yet, but you'll see. I'll do my best to try to look at what your equations are telling me and say, okay, yeah, they didn't put me a picture, and they should have, shame, but I'm not going to take any points off. I'll do the plus or minus. So I give a lot of partial credit for that. However, I'll also be very quick to notice if part of your equation says positive and the other part has the negative, and they don't match. I was like, well, obviously their answer is going to be wrong if they've got that sign wrong, which I'm seeing not a lot, but a few of that in the first problem. No, not the first problem. The problem you guys did, there was 2 football players, and some people started off by saying, okay, this is the positive direction for the running back, and then they come over here and they go, well, the safety goes that way, but they gave positive numbers for the safety, and they don't come up with a solution. Well, of course not, because if the running back goes this way and the safety goes that way, and the safety goes faster than the running back, they never meet. And so, yeah, there's no solution when you set up your equation that way, because you've set up your equations not to match the physical reality, right? So yes, signs are important, and understanding them, reading the map. Okay, good. So, but it does help. Back to your point, if you put the picture and it matches your equations, it's like you leave no doubt when I'm grading. It's like, oh yeah, that's 100% correct, no doubt. And that's obviously what you want to do when you're taking a test. Leave no doubt that I know it. All right, now continuing on, I would then label this as a positive x direction, so that again, everything is moving in my x direction. And everything is positive. And that, again, they don't have to be x and they don't have to be positive, but it does help to have them all labeled the same. And so now I can write out these equations. That's the step 3. So looking at this one, I would say M1G, pulling it down, positive, and minus T1 equals M1, and let me just call it A. There's no point in calling it A1 or A2. We already said they all have the same A value. In fact, let me put in my numbers here. This is a 4 times a 9.8 minus T1, and this is 4A. And I'll put a box around that as I'm writing out the equations. I'm not going to try to solve anything yet. That's coming up in step 4. But that right there has 2 unknowns in it, tension 1 and acceleration. And so that much I got out of this first one. Let's do the free body diagram here. And since this is going to have forces in the vertical direction, let me also just label which way I'm calling positive, and I might as well call up positive. There's no reason to do differently. But if I then write out my equations for this guy, and I'll do the x direction first, so I'll say sum of the forces in the x direction equals m2a. So in the x direction I would have T1 minus T2 minus the force of friction. And so positive, negative, negative. That's the 3 forces. And that has to equal to M2A. And if I put in what I know, which is very little for this problem, but it's T1 and T2. And here we come to that force of friction. Remember, the force of friction was the coefficient times the normal? And I'll do that because they did tell me the coefficient of friction was 0.35. So I will put 0.35 times the normal. And the mass of number 2 is 1. And I'll put a box around that. That's as much information as I know writing out that equation. It's got 4 unknowns in it, T1, T2, the normal force, and the acceleration. In fact, if I step back and look at it, isn't that the total number of unknowns I have? 4, right? T1, T2, A, and the normal force. So of course, how many equations am I going to need to solve for those 4 unknowns? 4, right? Now I'm not eliminating variables, I'm solving. So 4 equations for 4 unknowns. Okay. So I'm going to need 4 equations. Right now I have 2. But as you can see, I'm set up perfectly for 4 because now I can do the free body or the vertical direction here, and I can do it here. So it's going to give me 2 more equations for a total of 4. So let me write out the forces in the y direction. And in this case, there is the normal force going up, and there is gravity going down. And also, I can even tell you the value of the acceleration in the y direction, which is what? Yeah, 0, right? It does not accelerate in the y direction. It only is accelerating in the x direction. So this becomes a 0. So the normal force is equal to, well, I'll put m2g, but I can put those numbers in. That's a 1 and that's a 9.8. So that's a 9.8 Newton. So there's the normal force. Ah, that's great because I can put that right into there. Now, let me not do it now. I'm so tempted to start solving it, but again, I think it's best just to write out the equations. Make sure you have the ability to solve it. You have enough equations, you have enough information. And of course, you can see I don't have enough to completely solve it yet because, again, there are 4 unknowns here. And I've got equation 1, equation 2, and equation 3. Of course, I have another free body diagram, which is going to give me equation number 4. So the last step to do in this problem, or I should say the last part of step number 3, is to write out the equation for the free body diagram of this one. And again, notice that we're calling up positive. So this would be a T2 positive minus M3G equals M3A. And then putting in what I know the mass of this one is a 2. G is 9.8. The mass is 2, and there's an A. I'll put a box around that. And so there's the A and the T2. All right, so 1, 2, 3, 4 equations, 4 unknowns. And the first step would be pretty easy in the sense that I would just put the n into there. I guess then I would probably solve that for T1 and that T2 and put those into there, and then I can solve for A. But in the interest of time, I'm going to stop there and say, all right, now step 4 is solve these 4 equations and 4 unknowns. If it sounds easier, substitute that in. So it's 3 equations and 3 unknowns. Okay? And so there's no idea. Well, maybe we should try one more here. Got a few more on my list, but we better get into chapter 6 here and give you a chance then, because I think you're there now, is the best way at this point now is try it. Do it yourself. Keep in mind those 4 steps, and you'll begin to see that every problem is essentially the same problem. You're just adding up the forces, set it equal to MA. And when you begin to see that every problem is the same, you really are getting the point of the lesson. That maybe it's worth pointing it out again, right? You saw it on the top of the test, on the syllabus. You'll see it on top of every test. Physics is about knowing how to apply a few powerful fundamental concepts to explain a universe of phenomena. And so the concept is not that hard. I keep joking. You want all the answers to all the homework problems? There it is. I mean, how hard is that? F equals MA. That's it. Every problem begin with F equals MA. Now, it may take you 2 hours between when you start and finish a problem. And then, of course, you'll have many problems, so it may take you many hours. But if you just put together deductive reasoning, you will eventually get there. And you, of course, the bigger idea is you have just set yourself up for the idea that you could solve any complicated problem with forces, even if you've never seen it before. And so when it comes to the test or when it comes into a real world application after you graduate, you can kind of look at what's going on and say, okay, I've never done this problem before, but that's okay. That's what the physics is about, that this can solve that problem. Newton's laws of motion explain all motion. I've never done this motion before. I've never sent a rocket to Mars, but I can figure out how to get a rocket to Mars. And I'll just need this, this, and this, and there is the whole idea. All right, well, like I said, let's try yet another one here. I like this one. This one also has some friction, although it's static friction. And so again, it's going to make us think. But let's start with that step one. Get a good physical picture of what's going on. Then we can do the free body diagram. Then we can write out the equations. And then we can solve the equation. All right, so here's 44. It says a block of mass 3 kilograms is pushed against a wall by a force P. So I guess P stands for push. They got a little diagram right here. So here it is. You've got this object and it's up against the wall. Let's say this eraser, and it's against the wall and somebody's pushing on it. They're not pushing straight in, and they're certainly not pushing just straight up. They've got kind of at an angle here. And so that's this angle theta P they're trying to show here in the diagram. All right, with a force P, that makes an angle of 50 degrees with the horizontal as shown in the picture. The coefficient of static friction between the block and the wall is 0.25. A, determine the possible values for the magnitude P that allows the block to remain stationary. Describe what would happen if the magnitude of P has a larger value, and what happens if it has a smaller value. Then it says repeat this for 13 degrees. Well, we'll be short on time, so let's not repeat for 13 degrees, but let's just kind of set it up here. It says there's a range of values. Okay. Well, the goal here is to push so that the block doesn't fall. I mean, you can kind of imagine, what if I didn't push very hard? What if this was a small value? And if it got really, really small, wouldn't eventually this slide down the wall? All right, so I would say that there's some minimum value, right, of P. But on the other hand, what if I push really, really hard? Then it starts to go up the wall, right? So there obviously is some maximum. Okay, so that makes more sense now in the question where it says, determine the possible values of the magnitude. So there's a range. It could be somewhere between the small value, where lower than that it falls, up to the highest value, where higher than that it goes up. So not too much, not too little. It's what we call the Goldilocks force. It's just right. Not too much, not too little. All right, so that's kind of our range here. And there is something holding it up besides this push. What would that be? Friction, right? There's rubbing against the wall. And that I want to make sure you see before we go to the step 2 and draw that free body diagram. And so this wall is helping me hold it up, if you will. In fact, let's go to step 2 where it says, let's look at the free body diagram. And so if this is the block, and so here's the wall, what forces are in here? Well, as we said, there's weight and everything touching it. All right, so what's touching it? Okay, the wall and my hand. Why don't I go with the hand? That's the one I was thinking of first. There's the push. Okay, so all right, so we got gravity and we got my hand. And as you said, the wall. Okay? So what does the wall give me? What force is there? Is it up? Is it left? Is it right? Is it down?
Up and down?
Yeah, is there a normal force here? Yeah, what direction is the normal force? Right, perpendicular to the surface. And so one of the reasons I thought this might be a good one is the perpendicular to the surface doesn't necessarily mean up. And so I think you guys caught that right away there. Okay, but there is a normal force. But there's also something else, right? There is friction. And the friction is along the surface, which in this case is the vertical direction. So the wall is touching it. So not only does the wall have a normal force, but it has a friction. Which way is the friction? Is it up? Is it down?
Depends on the force.
Static. So it's
Resisting the hand and the gravity. Doesn't it depend on P?
Good. It does depend here. Watch. If I am barely pushing it, so let me say this is the minimum amount of force. The reason it's a minimum is because what is helping it stay up is the friction. You might say it's in danger of falling down. But on the other hand, if I am pushing it really hard, near its maximum value, what would you say about the friction then? It's keeping it from going up, right? And so that idea is, I think, what makes this a hard problem. You're going to need to say that the free body diagram are two scenarios. One time the friction is up and one time the friction is down. And again, I'll say it. The reason the friction is up here is because you are pushing with the minimum and it's in danger of falling down. You go any less than that, it begins to fall down. And that means the friction is opposite to the motion it wants to go. And in this case, if you're pushing it really hard, it's in danger of going up, so the friction is stopping it from going up. And so we're going to be able to do both of these. This one we're going to be able to solve and get the minimum value of P. And this one we're going to solve and get the maximum value of P. And that can answer our question, what is the range of P? Okay? And that's a big step into this one. So again, like a lot of these problems, you take that time to understand the problem as well as the free body diagrams. That's at least half the problem right there. Then of course writing out the equations and solving the equation, that's another couple of big steps in there. But especially the solving the equations, I don't feel like the students usually get trapped up in that. You've been doing, system of equations since algebra, and you've probably been doing algebra for at least 3 weeks or something, right? So you're pretty good at the algebra. That's not the tough spot. The tough spot often is setting up the free body diagram correctly and understanding the physics of what's going on so that when you write out the equation, you can write out the correct equations. And then, of course, solve those correct equations. All right, so I think I have it. I think I have the two scenarios. And so now I can go to step 3, which is write out my system of equations. So why don't we start with this scenario here and use a coordinate system. I see no point in changing from the traditional one, unless you do want to call the x direction, downward, because that's what it's in danger of moving. But I don't see a real advantage there. So I'm going to just stick to the traditional one here and say, let's use this traditional grid and apply it to this scenario and say, all right, write out the forces in the x direction, because that has to equal mass times the acceleration. Now, they were really nice to us. What's the acceleration in this one? 0, right? They want it to be stationary, has no acceleration. It is just stuck against the wall. Okay? And for that matter, whether it be the x direction, and I should have put x, or the y direction. It does not move in the x, and it does not move in the y. In fact, I would think if I kind of reduced my force enough, it would move only y, and it would still be a 0x. But in this case, we want to have just enough force that it doesn't move at all. So both of these should add up to be 0. All right, so again, let's come over here and look at forces in the x direction. The gravity and the friction are y direction, so I will ignore that one. But here I have a normal force, and the normal force is in a negative x direction. Here's a little more complicated. Here is the push, but it's off at an angle, so I would want a component. I would want the adjacent to the cosine. To the p. So I'll put p, and I'll put minimum. Cosine theta minus the normal would equal 0. And so that would be my first equation writing out in the x direction. Writing out that equation in the y direction, I would say, okay, I have a frictional force going up. I have a gravitational force going down. The normal force is only in the x direction, so I don't have anything from it in the y direction. But again, here's the more complicated one. The push has components, and so the push here does have a positive p sine theta equals 0. Now again, let's talk about the static friction. Maybe it's worth writing it over here. The static friction was an inequality, right? It was less than or equal to the coefficient of static times the normal force. Now, if I am going to give the minimum push, doesn't that occur when the friction, which is helping me lift it up, is at its maximum? So I would say the static friction is equal to that number at that point. If I was pushing a little bit more than the minimum, then the static friction would be less than that number. But since I'm trying to solve this problem for what is the minimum push and eventually the maximum push so I can get the range, then I'm going to go ahead and set the static friction to its maximum value. That will help me solve for the minimum push. Okay, so I'm going to come over here and go coefficient of static friction times normal mg plus p sine theta equals 0. And I think they gave me the coefficient of this, right? Yeah, see, there it is. Between the wall and is 0.25. So that is the number that I can substitute in. And in fact, now you can begin to see why it was important to do both dimensions. This dimension gives me the normal force. So I can start to solve this by saying normal force equals the minimum push times cosine theta. And once I know that one, I can put it in here. So this is coefficient of static friction times the normal, which would be P minimum cosine theta minus the mg plus P. And I probably should have put P minimum here, minimum, to make it clear, this is the minimum push, and that needs to be multiplied by sine theta equals 0. And so if I rearrange this equation, I can put the mg over here, making it positive. Each term has a p minimum in it that can be factored out. And so solving this for p minimum would be then mg over the coefficient of friction cosine theta plus sine theta. Yay! There it is. Okay. And so we've done some pretty tough ones today, and hopefully you're beginning to see that I don't think you would ever guess this as the equation, right? And so again, remember the strategy here. It's not try to guess and figure out the equation at the end. It's just write out the equation. It's really that simple. And then a lot of deductive reasoning, and you get to something very complex. Especially that one that we had the movable pulley and the blocks at the different speed. I mean, those equations were, you would have never guessed that 4 was in front like that. Okay? But this is the equation. Now, again, just to save a little bit of time, let me not punch it in, but I think they gave me all that. Let me just double check. They gave me the mass, good. They gave me the coefficient of friction, and they gave me the angle. And so I can put all those in and find out what the minimum is. I'll even save a little bit of more time so we can get started in chapter 6. I'll change to a color green. What about the second one here? What would be the maximum push? What would be different? Well, I hope you're seeing that, yeah, everything is the same except for the friction is in an opposite direction. But we would still argue that your maximum push occurs when your friction magnitude is equal to this, right? Because as you start to push more and more and more, it doesn't go up because the friction increases more and more and more until the friction gets to its maximum. And then once the friction gets to its maximum, then if you push beyond that, you begin to push it up the side of the wall. So coming in with a different color, I would say if I'm going to add up my forces in the x direction, I would have the word maximum here, but it still would be cosine of the angle, and there would still be a normal force, and it would still equal 0. So when I go to solve this for the normal force, nothing there has really changed other than now it says P maximum instead of P minimum. The y direction is where the big change occurs, because what would you say here? Negative. Yeah, I would put a negative out in front. But gravity would still be down, and there would still be an upward force. I might put a maximum here instead. But translating that down to the next line, I would just have a negative in front with a maximum. And as I put it into here then, I would still have a maximum but with a negative there, and this word here would be maximum. And so everywhere I see minimum, I'm going to put maximum, and everywhere I see the coefficient, I will just put a negative. There it is right there. So there would be the answer if I did the same steps for the maximum. And of course you could now see why mathematically it would give you a bigger number, because you are, instead of adding these together to get a big denominator, you subtract them and get a smaller denominator. And a smaller denominator gives you a larger quotient. So this would be a larger maximum force. Well, with that said then, let's take and move into chapter 6. We have, about 40 minutes left here in class. And so let me take this as an opportunity to introduce you to the concepts in chapter 6. The good news here is there are no new fundamental concepts. We're going to do exactly the same. We're going to use this chapter to do more of Newton's laws of motion, particularly this second law and those 4 steps. And so probably the best thing I can say here is, there's no new learning to do. They're just different types of problems. As I said a little bit ago, none of the problems we've just done here in Chapter 5 actually involve an object that is turning. And so Chapter 6 does that. In fact, Chapter 6 is trying to do 3 concepts that we have not yet done. And so my lecture on Chapter 6 is not very long. We got 40 minutes, it's about perfect time. I would like to do some examples for you, so on Monday we'll come back and do lots of examples from Chapter 6 before we get started into Chapter 7. But let this be a way of saying you have the skills right now to do Chapter 6. So if you have finished Chapter 5, continue on into Chapter 6. Okay, that next test can come up pretty quickly here. In fact, here is the title of Chapter 6. Chapter 6 says it is Newton's 3 laws continued. And so, like I said, I'm not going to really give you any new fundamental physics. We're going to just do the same 4 steps. Our problems will be a little different. I would even say more complicated. Because your author says, let's look at 3 cases that we did not look at in Chapter 5. The first one is let's take a look at objects that are turning. We'll call it circular motion, but it may not make a whole circle, right? It may just go a part of a circle. But that would be a turn. And so if I'm driving my car and I, have a fork in the road, during that part, I am doing part of a circle. And so that we haven't really dealt with as of yet. But we will here. So I'll call that circular motion. Another fun one to discuss is what do we do if we are in an accelerating object? Do you remember when we introduced Newton's 3 laws of motion at the start of Chapter 5? And I know it was before the test. But I said Newton's 3 laws of motion are valid except, and I gave 2 cases when we got to be careful with them. What was the first one? Yeah, it was the one that what if you're an accelerating reference frame? And so we should probably talk about that a little bit, and that's what your author says. What if you are actually in the accelerating frame? Okay, and so we'll continue on with that discussion. Of course, maybe in passing I should mention, when else did we say Newton's laws weren't? Yeah, we start getting real fast. When we get as fast as 10% the speed of light, which is an enormously fast number. So that was not, most of the time, it's not a necessary issue. And so Newton knew what to do about the accelerating reference frame, and that's what we're going to talk about. But he didn't know about the close to speed of light. That took Einstein. And then the third thing we'll talk about is what we refer to as more friction, just to kind of distinguish it from the solid to solid friction that we've been doing. We'll call it a resistive force. So we've been doing frictions where 2 objects rub, but they're solids rubbing on solids. What if I had a solid, such as a baseball, moving through the air? Isn't there rubbing going on between the baseball and the air? But it's not solid to solid, and a lot of different behavior occurs, and so we should talk a little bit about that. And you'll see it starts to get real complicated right away, so we'll only talk a little bit about it and save more of that for later on in your formal education here. All right, so I'm going to talk about things going in a circle. The reason this can actually be a short lecture is right here. Didn't we already deal with things moving in a circle on chapter 4? I mean, to some degree. We didn't have forces, but we had acceleration. I know you saw one on the test. Didn't you have one going in a circle on the test? Right? And the thing we learned in chapter 4, and hopefully you remembered for the test, and if not, let me repeat it here, that if you have, let's put this as the center of the circle, and you have an object that is moving, say, in this direction, V, maybe I'll change colors, doesn't that object have a radial acceleration? Doesn't it need an acceleration in order to turn? Wasn't that our whole discussion in chapter 4? And didn't we go through a little proof that said the radial acceleration would be equal to? Yeah, V squared over R. And so again, that's what we learned in chapter 4. But we also learned in chapter 4 that this makes it turn, but it could also be going faster and slower, right? So let's say the object was going slower. What else would be happening besides having a radial acceleration that is making it turn? It would also have a tangential. Which way would it be here to make it go slower? Opposite that it's moving. So then it would have a tangential piece, right? Where we said the tangential piece is the part that changes its speed. Now notice so far I haven't said anything that we didn't already learn in chapter 4. I'm just kind of repeating what we did in chapter 4. I'm also going to repeat what did we learn in chapter 5. Well, in chapter 5 we learned if you added up all the forces that would have to equal mass times the acceleration. And so this first two sections of chapter 6, and like I said, why they're easy for me to explain, don't get me wrong, the problems are still hard to do, but it's very easy to explain because let me just put those two things together. Here's what it would say. To add up all the forces in the radial direction, what would it equal? Right? It would have to equal mass times the acceleration in the radial direction, which is V squared over R. And if I were to add up all the forces that are pointing in the tangential direction, what would it equal? Mass times the rate at which its speed is changing. Exactly. And so your author talks about just turning without changing its speed in section 1. And in section 2, he writes out, well, what if it is also changing its speed? And so now that we've just done chapter 5, you're getting real good at adding up all the forces and the components. If it helps, I often do this in the problems. I just pick my grid and I call towards the center of the circle X and tangential to the circle Y. And then I don't have this funny notation. I can write this as the forces in the X direction equal to mv squared over R. And the forces in the Y direction is m times the change in speed, the rate at which it is changing its speed. And so you'll see as we get to some example problems, which won't be today, but it'll be Monday, is we will have a scenario, we'll put it up here, and we will add up all the forces. And maybe there is 5 forces, maybe 3 of them have components in the x direction, so if I add those 3, I know it has to equal to mv squared over r. That's the point. Okay? And so, again, you can kind of see why I'm trying to say here is I'm not really going to do anything new in this chapter. I'm just going to spend 40 minutes talking about 3 different scenarios that we essentially are ready to do. We just need to do them. They're not easy scenarios. They're harder than the ones we did in chapter 5 where things were just going faster or slower. But this is how we do something turning. And so we can have turning and turning with a change in speed. Your author calls this uniform circular motion and non-uniform circular motion. And so that's going to be our first case. Yeah?
Are we going to find like the sum of the forces, like so the total acceleration?
Right, okay, so at risk of going too far into an example and not waiting till Monday, here might be a scenario where I have a ball on the end of a string, and as I look at the forces, then there would be a tension T, and so here's a circle, and when it's right here, there would be an mg. And so if I call inward the x direction, and I call this an angle theta, I would say, as I add up all the forces in the x direction, I would have tension, and I would also have mg cosine theta, right? So there's kind of the simplest scenario I can think of, a ball on a string. It's got two forces, and one of them, all the forces in the x direction, and the other one, a component of it, is in the x direction. That would have to equal mv squared over r. That's my point.
Okay.
So add up all the forces. If I did the y direction, did I do something wrong?
Yeah, sine theta.
Oh, yeah, so in the y direction, I would have an mg sine theta. That would have to be connected to how its speed is changing. And as you can imagine, a ball spinning here on the end of a string, as it is coming down, it probably would be going faster, right? Gravity is making it going faster. So it's this component of gravity that is making going it faster, and it is the tension and the component that is making it turn.
Okay.
So
I guess my question is, like in the lab in like chapter 4 or whatever, there was like a total acceleration where you found all the components of the acceleration to one total acceleration.
okay, right.
And then would we have to like use that to find like a total force? Acceleration in the x direction and the acceleration in the y direction and all its components.
Right, okay. Perhaps. It depends what the question is asking. In this case, if the question was, say, find the tension given these other parameters, then I would want to leave it in its separate components to find the tension.
Okay. So you would, okay.
But on the other hand, if you were to ask me what is the total force, and I'm given the tension, this would be its x component, so I'd square it. This would be its y component, and I would square it. I would add it together and then get the total force. Yeah. Yeah. All right. Good. Great question. But again, let me just kind of leave that one alone for a moment. Let's talk about the other two scenarios we are going to look at. So, taking that, let me kind of clear this off and say, let's look at the second option we will come across, which, by the way, will be section 3. And we have a real easy answer for that. Let's talk about it a little bit more like we did in chapter 5. I think the best way to do it is to show you with the pictures that your author gives you, because he started this in chapter 5, but he continues it more here in chapter 6 about accelerating reference frames. And he says, somewhere in here, you can kind of see the pilot circular. There's a non-uniform circular motion. I think it's the next page. There it is. Where he says, let's imagine ourselves in a train. Okay? Now, the reason the train is because the train can be pulling out of the station and accelerating. And if you are in the train, we said that be careful using Newton's laws of motion because you are in an accelerating reference frame. And so let's talk about the dilemma here. And they show a boxcar with this hanging from the ceiling. Maybe it's a dining car and it's the chandelier. And it's hanging down here, but we have two observers. One observer is standing outside in what we would call an inertial reference frame, whereas the other person is inside the boxcar. Here is what I tried to say in the last chapter and want to repeat now, is this person can get a misunderstanding of what is going on because this person is in an accelerating reference frame. If they see the chandelier angling back a little bit, this person kind of looks at it and says, well, what are the forces on the chandelier? And if they follow the Newton's laws as we were talking about, they would say, well, there's gravity pulling it down and there's tension pulling it this way, but why does it swing backwards? Well, it swings backwards because something's pushing it that way. Well, is there really something pushing it backwards? No. I think the best view is this view. Here's somebody outside. If you watch somebody on the outside, they would say the train is taking off. So what happens is the chandelier angles back so that the tension can have a component in that way so that the chandelier can accelerate with the train. And so the best way to solve this problem is to say that if you have your boxcar and you're standing in a non-accelerating reference frame, you will, without question, agree that the chandelier swings backwards because the free body diagram would look something like this. Gravity is pulling it down. The tension has some angle so that when I add up the forces in the x direction, I would have T sine theta equals ma. I would have a component in the x direction. The chandelier will actually accelerate. That makes complete sense. The person on the outside is the one who I would say is viewing it correctly. He's viewing it, or she's viewing it, as implied by Newton. However, it's the person on the inside that Newton warned us about. He said, look, don't try to take and apply Newton's laws from the perspective of the person on the inside. Because the person on the inside would say it's stationary. Unless, of course, they realize they're in a train and accelerating. And that's my point I want to make with you. Don't try to analyze the problem by being in the boxcar. If you come to a problem and it's talking about this train and it's moving, don't put your viewpoint from in the boxcar. It doesn't work. Viewing it in the boxcar, you're going to think because the object is stationary, there must be an additional force that way. But of course the chandelier is not really stationary, which of course is why there is not really a force going the other direction. And so Newton said we have two options here. If you want to analyze this from the person in the boxcar, either one, get out of the boxcar. And that's the approach I'm going to take. Just get out of the accelerating reference frame. Never view it from in the accelerating reference frame. Another option is we can create a fictitious force and then say the acceleration is 0. And believe it or not, those can be very useful times. But I think for the beginning student, for you guys, the best thing to say is let's not do it that way. Let's just get out of the boxcar. Okay? And as your education takes you a little bit further, just remember that we could actually analyze it from in the boxcar, where Newton said we shouldn't, if we also invent fake forces, which aren't really there either. So we're making one error to correct for another error. And I know it sounds ridiculous at first. That's where I want to leave it. It's ridiculous. Don't do that. But on the other hand, don't be surprised if later on in your education you view it from what we call non-inertial reference frames. Watch, let me give you another scenario. This is the one scenario. Your author also talks about kind of this vantage point. Imagine, if you will, two people sitting across from each other on a round table, but the table spins. And so it doesn't really show it well here. We need kind of an animation of this thing spinning. But let's say this is you. They're trying to say if you're right here, then your friend is straight across from you. And if you take the ball and you push it straight to your friend, what will happen? Well, from somebody who is standing outside, not spinning, because if you're spinning, you're accelerating, right? So to do Newton's laws correctly, wouldn't we want to be outside? And Newton's first law says if you give it a push, doesn't it go in a straight line if there's no other forces? So he's saying with no other forces, so there's no friction on this table, if you roll the ball, doesn't it roll in a straight line? But does your friend catch the ball? No. Why does your friend not catch the ball? Because really your friend has moved, right? That's what I would say. Newton's laws were valid. Newton's laws said, look, it goes in a straight line. But because this whole table is spinning, you pushed it here. By the time it gets over to here in a straight line, you have moved here and your friend has moved there. So no, your friend hasn't caught it. But you said, well, wait a minute. From my viewpoint on the table, didn't I throw it straight at my friend? Shouldn't it go straight? And yet I missed my friend. Well, of course, as I'm trying to say, hopefully the obvious point here is the object really did go straight. But yes, it misses your friend because your friend moved with the table. So this picture is trying to show what it might look like from your perspective. You would be right here and you would throw it to your friend. Yet, as it goes towards your friend goes that way and the ball goes that way. And so from your perspective, it looked like it curved. Now, of course, what I'm trying to say is there is not some kind of force making it turn. But according to Newton's laws, shouldn't there be a force to make it turn? So what's wrong here? Well, what's wrong is you are in an accelerating reference frame. You are trying to apply Newton's laws when you're in an accelerating reference frame. Don't do that. That is a no-no. That is what we said in chapter 5, and we're really kind of driving home now, is if you ever find yourself trying to analyze the motion of this ball, do not do it from the viewpoint of somebody on the table rotating with the table. Step off of the table and view it from outside. This is a better view than this one. If you do it in this view, you're going to think there's some kind of magical force turning it, which is where we get that word Coriolis force. And we say, oh yeah, if you shoot a cannonball on the earth, because the earth is spinning, it will, well, I guess it spins the other way, goes to the right. And you go, oh yeah, the cannonball moved. Why'd the cannonball move? Oh, there's some Coriolis force. No, there's not. It's not that the cannonball moved. It's that the earth moved. Cannonball went straight. And if you were to stand out of the earth, if you were to be the little alien out here looking down, you would see the cannonball went straight. It's just that the earth was rotating, and so the person you were shooting the cannonball at has moved. And so it's not that the cannonball moved away from the person, it's that the person moved away from the cannonball. And so again, just have to be a little bit careful on how we analyze it. So again, not really much work to do here at a lecture, only just to give you that warning again and again. Warning, warning, warning. Be careful on the problem they give you. They give you need a force, right? And this kind of silly picture is kind of showing it. From the vantage point of inside of the car, here's the person, and the person feels like they're being thrown out of the car. There's the fictitious force. There is no centrifugal force. There's nothing throwing you out of the car. The reality is you're just trying to go straight. Newton's first law. You're in motion, you want to continue in motion. But the problem really is that the car is turning, and so you need a force towards the center of the circle to turn. So the better view, or at least the view we will take here, is what ends up happening is you need a force pushing you in. And so that's why if I wasn't reading my physics book and paying attention to the road, I've ridden in a car so much that I probably, when I see that turn, will kind of lean a little bit or pull on the seatbelt or nudge on the door or do something that I don't even realize I'm getting a force. And I think, oh, I don't need a force to make a turn. No, that's wrong too. You need a force to make a turn. That force comes to you. You're just so used to driving in a car. Dogs aren't. Don't try this, but you put a dog in the car for the first time and you make a turn, they're all over the place. They had no idea that they were supposed to lean or turn. They just, they're just happy to be there, and then all of a sudden, whoa, and they're up against the side door there. Okay. And again, that's a really good example of what is really happening. So I'll say it again. Here's going to be our approach. This second scenario here, when we are dealing with accelerating reference frames, just get out of it. So if you're in a car that's turning, analyze it from outside the car. You're in a boxcar and a train that's moving, get out of the train. You're on a turntable, get out of the turntable. Analyze it from outside. And then once we do that, we can apply Newton's laws of motion, and all is good. So there's scenario number 2. Scenario 3. And see if we have just enough time to get scenario number 3, which we'll call resistive forces. Maybe I'll even call this air friction, because like I said, a baseball going through the air would be a good example. But it's not the only one. This could be a rock dropped in the ocean, right? As long as we have a solid moving through a fluid, it's pretty much the same physics. So I will say, let's just take a baseball and drop it. And if I do a free body diagram and I say, okay, here's the baseball, what forces are on the baseball when I drop it? Well, obviously there's gravity. There's gravity in anything touching it. So what's touching it? Right, and so for the first time, let's include air resistance into our equations. We have ignored that, and of course, hopefully you saw that on your, chapter 4. We always kept saying, neglecting air resistance, not important. Well, let's change that now. Let's study what would happen. And so what I'll do is I'll put then a little r up here. And maybe we should talk about its direction. The R, of course, stands for resistive force. But if I make these little dots, which I'm trying to represent the air molecules, or this could be water molecules, but as this object moves through the air, doesn't it have to push the air out of the way? So here's Newton's third law. If the baseball puts a force on the air, what does the air do? Puts a force back on the baseball. And so there's our resistive force. That's the cause of it. The fact that the object has to move through. If this is a dolphin going through the water, doesn't the dolphin move through the water? Doesn't have to push the water out of the way. So there's a resistive force as the object moves through the water. Now, if you made a plot of this resistive force versus speed, quite interesting effect takes place here. And maybe you can begin to see it. Let's say I'm going at a slow speed, like 0. So I have a dolphin that's not moving. Well, how much resistive force does it have? 0, right? Doesn't have to push any molecules out of the way. It's not moving. But let's say it goes at a small speed. Then I would say it probably has a little bit of resistance, because as it moves through, and even me just walking, moving through the air, don't I have to push the air out of the way? Push the air out of the way. Okay. Now let's say I go a little faster. I go twice that fast. Do you think I have the same resistive force? Yeah, here's where it gets more complicated, and why we didn't do this in chapter 5. We were waiting a little bit. See, when we did solid to solid friction, we said the friction was the same regardless of how fast it's going. But I would say if I am going twice as fast, maybe there, I would have to push twice as many molecules out of the way, and hence I would have twice as much resistance. What if I went 3 times as fast? Yeah, I would get 3 times. Now what if I went 4 times as fast? Except something interesting begins to happen when I get even faster. Because when I'm going relatively slow, all I'm doing is kind of separating the molecules, and then they come back together. But what do you think would happen if I was going fast?
Could you like create a vacuum
Okay, and?
and move like
So
less?
they come with me, right?
Oh, okay.
I start bringing them with me. So it's more than just moving them out of the way. So when you go really slow, you just separate the molecules and they regroup behind you. And that's why if you double your speed, you hit twice as many molecules. But I would say if you go really fast, not only do you hit more molecules, but then you drag them along with you. And then, let's say that is some speed v1. What if I double that speed? Now, I would say when I start getting up to this speed where I drag them with me, when I double the speed, not only do I hit twice as many molecules, I'm dragging with me twice as many. So twice as many molecules with twice the amount dragged along is 4 times more. And so I would say it begins to go like a parabola at that point. If I went 3 times faster, not only would I hit 3 times more molecules, but then as I hit them, I would be dragging with them 3 times more. So it'd be 3 times 3, 9 times. Here's what I'm getting at. What I'm getting at is the resistive force is either proportional to the speed or it is proportional to the square of the speeds. We kind of have 2 scenarios. We have one scenario where we are going slow, and we have another scenario where we are going fast. And so that is, well, a good first step here, yeah.
At a certain point, will the second equation for fast speeds, will that ever plateau back out? Or will that always stay consistent?
And no, and then it could get even more complicated. Yeah, it can get really, really complicated. So I should emphasize this is an approximation of what will happen. It's not the whole story. It's enough for us to get started. But what we call fluid dynamics can get real complicated. To solve it, we have to have a lot of differential equations, which is why you guys will take your fluid mechanics and fluid dynamics once you transfer. It'll be one of the first classes you take when you transfer, but you have to take your Math 220 before you can really do justification to this. So what I'm saying is this is an overly simplification of the air resistance, but it's enough to get some really advanced and complicated problems. It's a good first step. Complete? No, but a good first step. Let me put one more thing before we kind of wrap it up here for today. And then we'll come back to talk about this more on Monday, and then we'll be done talking about the chapter. I told you there's not a whole lot more to chapter. But so far, I've only mentioned the resistance based upon the movement of it. Shouldn't there be other factors in here for this B? What else do you think would contribute to the air resistance?
The friction on the object.
Yeah, but what, and this is the R, so this is the total friction. But the part of it is certainly how fast it's going. And that was the main thing I wanted to discuss. But it's not the only thing. Don't you think it would depend on how big the object is? What I'll call the cross-sectional area of it. Because isn't that really telling you how much air it has to push out of the way? And so as you hit it, if you have something that more is long and skinny, it doesn't have to push much water out of the way as compared to something that's big and fat, right? The cross-sectional area of it. So not a surprise that something that has more cross-sectional area would have more resistance. I think that makes sense. It also makes sense of why, if you've seen the shape of a dolphin, the shape of a whale, the shape of a submarine, aren't they long and skinny, kind of this hot dog or cigar look? Because the idea is you want a lot of volume to it, like say a submarine, but you want to be able to go through the water really well. An arrow is another good example, right? Long and skinny, because it's only the diameter of the arrow that actually has to push any air out of the way. And so that cross-sectional area. When it comes to automobiles, you can imagine a big old van has to push a lot more air out of the way than a little tiny sports car. And so the cross-sectional area is important. Also, since we're low on time, I'll just put this out here. Not a surprise, maybe, is the density. The density is, of course, how much you're pushing out of the way. It's a lot harder to go through water than it is air. Make sense? You got to get water and push it out of the way. They're heavy. There's lots of molecules. Air, much easier. And in fact, the higher the altitude, the less air. So why do all of our airplanes fly at 30, 35,000 feet? What's the point?
Easier.
A lot easier. If you're going to fly from Los Angeles to New York, there's very little air resistance. Well, they're going really fast though too. But the density is so low, you can cruise through the air. If you stayed at 10,000 feet and were flying through the air, you'd run out of fuel. You'd have to land in, say, Chicago in order to refuel, in order to keep the process up. And so it would be very expensive, and you would burn a lot of fuel here. So the density is very important. For you sports lovers, what stadium hits the most home runs? Colorado. Why? Altitude's mile high, right? A 400-foot fly ball would be an out on the warning track, is way over the fence at 425 feet with the lower density. And so it can make a big difference there. D, I will just say this is the shape of the object. The fancy word we like to give is its drag coefficient. And so kind of makes sense that something that is got one shape versus another can slice through the air a little bit better than the other ones. And so it's really kind of a multiplication factor of how well does this area slice through the air. There's one more, a half, which we can ignore or put there, but you'll see in a little bit the half is going to be nice. We throw that in there because it's going to match our kinetic energy, 1/2 mv squared. We haven't done kinetic energy for this class, but if you remember it for 102. So those would be the other factors. So there's 4 factors of why there's resistance. How fast are you going? How big is the object? What shape is the object? And what is the density of the material you're going through? Well, more on this on Monday. Good luck on the homework.